This is probably one of my favourite topics on the A-level specification, is differential equations. And the differential equation is an equation that contains at least one derivative term. Okay, now it might be the gradient term, or it might be a higher order derivative. So, for example, you might have dy by dx times e to the y equals sine of y. There we go, that's a differential equation because it's an equation which contains a derivative. Or we might have y plus d2y dx squared equals 0. Again, that's an equation and it contains a derivative term, so therefore it's a differential equation. And there are many examples. I mean, we've seen something like this in year 12. This is actually a differential equation because it is an equation that contains a derivative, but we know how to solve this one from year 12 maths. And all we do is we integrate both sides with respect to x to get a solution. But there are more complicated ones. For example, this one here. dy by dx is not just a function of x anymore, but a function of x and y. So we will look at how to solve this type of differential equation in this video. Or we might have a second order differential equation. That's a differential equation that contains a second order derivative. And we look at solving those on the further maths course. We don't look at solving these on A-level maths at all. Or we could even go more complicated. And we have dy by dx multiple times. Here it's outside of everything, just times by x squared, but here it's inside a sine function. So there's no way to actually solve this differential equation unless you use a numerical approximation to do so. And there are many other types of differential equation that we could get. Okay, here we go, we've got another differential equation there. Or we can have a third order differential equation, like this one, where we've got e to the power of a derivative is some function of x, y, and y triple prime. So this is a third order differential equation. And I'm not even going to attempt to begin to look at that. It looks horrendous. Fortunately, on this course, it is very much an introduction to differential equations. So the ones that we meet will be fairly straightforward and always solvable. Okay, let's have a look at number one. Let's have a look at the method that we do. So what we do is we start with f of x, y, and dy by dx. So we only ever solve first order differential equations on this course. In other words, you'll never find an equation that contains a second order derivative or higher. And what we do is we can rearrange it into dy by dx equals g of x times h of y. So it's a product of two functions, one in x and one in y. Now this is always going to be true on the A-level course. It's not always true in general. Okay, in general, you can't necessarily do that, but on the A-level course, we can because of the form of the differential equations take. And what we can do is, once we've got this, is we can use the method of separation of variables. And occasionally a question will give it to you in this form already, so you don't have to do any rearrangement. And the separation of variables is what it says on the tin. It takes the two variables, in this case x and y, and it separates them and put all the x on one side of the equation and all of the y's on the other. So if I take this function of y and bring it to this side, and this dx and bring it to this side, I'll end up with 1 divided by h of y dy equals g of x dx. Now I've cheated a little bit there because I've treated this as a fraction, which is not actually a fraction. It just behaves like a fraction in every sense of the word. But then what does this mean? What does 1 over h of y times dy mean? It doesn't mathematically mean anything. And this line is actually completely nonsense as it currently stands. But I can do something very simple to both sides to make it make sense. And there we go. Now it makes sense, because I'm integrating a function of y with respect to y, and that's going to equal the integral of a function of x with respect to x. And this is going to give then the solution to the differential equation. Let's see this in action. So we've got dy by dx is equal to sine of x divided by the cosine of y. So what we're going to do is we're going to separate the variables. We're going to times both sides of the equation by cos y to bring this up to the left, and we're going to times both sides of the equation by dx to bring this up to the right. Multiply by cos of y dx. So that's going to give me cos of y dy equals sine of x dx. It doesn't make sense mathematically, so to make it make sense, we now put in our integration symbols, and now it does make sense. Now we can integrate the left-hand side, and we can integrate the right-hand side. So the left-hand side is going to integrate to the negative sine of y, the positive sine of y, because cos integrates to positive sine, and sine integrates to negative cos. That's going to go to minus cos of x. And then, because our two integral symbols have now disappeared, we can now replace that with a plus c. And we only need one constant because it's arbitrary. If you add a constant to this integral and add a constant from this integral, you can just combine them together to give you one lone constant. And we only need one constant because the differential equation is a first order differential equation. So this is the solution to this differential equation, and I could rearrange that to give sine of y plus cos of x equals a constant. Okay. What I'm going to do now is just show you a solution to this differential equation. So I'm going to sketch this curve for a particular value of c. This is what it looks like. It's just a load of circles, or weird shaped circles. And as I vary that plus c, when it was an explicit integration, i.e. dy by dx was a function of x only, then as you varied your arbitrary constant, it just moved the graph up and down. But now, because y is not a function of x, it's implicitly defined, this c is going to do some weird and wacky things. So as I vary my constant of integration, in this particular case, this happens. Now, all of these are solutions to the original differential equations. Every set of curves satisfies the differential equation. But you can see the graph is not moving up and down anymore. It's doing this weird thing. I can't even describe it. And that's not uncommon when solving differential equations. Okay, we get some peculiar happenings as you vary the constant of integration. And that's the solution. That's the answer to the question. Okay, example number 2. dy by dx is equal to x y squared e to the x. So again, we're just going to separate the variables. So I'm going to get y to the minus 2 dy, okay, but dividing both sides by y squared, and that's going to equal x e to the x dx by timesing both sides by dx. So what I've done there is I've times both sides by dx divided by y squared. Okay, that'll get rid of the y squared on the right, and that'll get rid of the dx on the left. That gives me this. That doesn't make sense until I put in my integration symbols, and now it does make sense again, and I can just carry out the integrations on both sides of the equation. So add 1 to the power, divide by new power, I'm going to get minus y to the minus 1. And for this one, I'm going to need to use an integration by parts. Okay, so everything you've done in integration so far, any of it can come up in these questions. So just to remind you, integration by parts says the integral of uv primed dx is going to be uv minus the integral of vu primed dx. Okay, that's the by parts, and that is in the formula book. So in this case, I'm going to set u to be x. Okay, don't forget the late rule. There's no logs, so the u is the algebra. U prime therefore is 1. V primed therefore is e to the x, and then if we integrate that, we'll get e to the x. Now we take those definitions and we plug it into the integration by parts formula to get the right hand side. That's going to equal uv, which is x e to the x, minus the integral of vu primed, which is e to the x dx. I can carry out that integral now straight away. So I get x e to the x minus e to the x plus a constant of integration, which I introduce at this stage because there's no integration symbols left. Okay, and this is minus y to the minus 1 equals. I'm just going to factorise out that e to the x. There we go. And now if I make y the subject, I can do that by timesing by minus 1 and then reciprocating. So I get y is going to be equal to 1 minus x e to the x minus c, all divided by 1. Okay, so times by minus 1, so that went from x minus 1 to 1 minus x. That went from plus c to minus c, and I've reciprocated because of the power minus 1, so it's now 1 over. And what I can do is I could change that to a plus because this constant is arbitrary. So I could put a plus c there and maybe put a plus c0 just to make sure it's different to that, and then redefine my arbitrary constant. So I'm going to say c0 equals negative c. And you don't have to do that, but it does just look a bit nicer. Okay, so let's have a look at what this is going to look like. So again, plotted some curves, and I can vary the arbitrary constant here, and we can see, zoom in a little bit, there we go, see a little bit clearer what's going on there. It's not moving the graph up and down anymore, it's doing this weird timesy thing, and the asymptote is moving until it becomes viable and then disappears again. So all of these are solutions to the original differential equation. Every curve that you see is a solution to the differential equation. Which leads me on to, well, what about a particular solution? So at the moment, what we have found is we've gone from a differential equation, which is a function of x, y, and y primed in our case, and we've solved the differential equation, and that's given us y as a function of g of x and an arbitrary constant c. Sometimes, maybe you might have a function of x, y, and an arbitrary constant equals 0 if you can't make y the subject. So you might have that. But if you can make y the subject, then this is going to be the kind of the general case, and every value of c will give you a solution to the original differential equation. So this is an arbitrary constant. This is what we call it, an arbitrary constant. This and that, if you can't make y the subject, we refer to them as general solutions. And what they represent are the family of curves which satisfy the original differential equation. Every value of c will give you a solution to the differential equation, and every solution to the differential equation can be expressed as this or this for a given value of c. But what happens if we want a particular solution? So say we're given some more information. So say more information is given, like when x is such and such, then y is this thing. Then what we can do is we can use this knowledge in conjunction with the general solution to find a value for c. And once you've found a value of c, then you end up with y as a function of x, or you end up with h of x, y equals 0 if you can't make y the subject. And there's no arbitrary constant anymore because you found a value for it, a numerical value for it. And this is what we refer to as a particular solution to the differential equation. Or again, if you can't make y the subject, that is also a particular solution. And it's a particular solution because it is one of infinitely many solutions to the original differential equation, but it is the only one that satisfies the particular condition that is given. So let's have a look at a couple of examples of particular solutions. So dy by dx is this thing, y times cos of pi x times pi, and we're now told that when y is 3, x is 5. So again, I'm just going to solve this differential equation. I'm going to get 1 over y dy, integral of, is going to be equal to the integral of pi times the cosine of pi x dx. Okay, so that's separating the variables. The left-hand side becomes the natural log of the mod of y, and the right-hand side is going to become sine of pi x. Now the integral symbols have gone, we can add that plus c. Now I can make y the subject by raising both sides as a power of e, so that's e to the sine of pi x plus c, which I could then write as e to the c, e to the sine of pi x, which is a e to the sine of pi x. And I've defined a to equal e to the c. And I can do that, I can redefine my arbitrary constant to give that. And now I can use my condition. So I'm told that when x is 5, y is 3. So that means that this must satisfy the equation, the solution. So if I plug in y is 3 and x is 5, okay, x is 5 is going to be sine of 5 pi, which is 0. I end up with 3 equals a to the 0, and that tells me that a is the number 3. Or if you kept it as c, then c would be log 3. And that would tell you the particular solution to the differential equation is y equals 3e to the sine of pi x. And that's the particular solution. That is the solution that goes through the point 5, 3. Let's have a look at that on here. Again, you've got some quirky things that happen as you vary the arbitrary constant. In this case, it kind of stretches a little bit in the x and y directions. And there's one curve that'll go through my point of interest. Only one of them will match it, and that is when it is 3. All the other curves miss it. That's above it, that's below it. There's only one that goes through it, and that's when the coefficient is 3. Okay, I'm a little bit short on time, so I will do number 4 in a separate video. But have a go yourself, see if you can get the answer to that. It is x plus 1 all squared times 3x plus 1 times dy by dx equals y times 12x squared plus 23x plus 9, and it goes to the point 0, 5.